Hello and welcome to chapter 15 about light. Light is one of those subjects that it's not going to say a lot about in the book. We're basically just going to give a quick presentation of what light is and what different wavelengths of light do. But it is incredibly important in our day-to-day lives. Light is a property is both a property of electromagnetism and just which, as you can guess, also has which, as you can guess, also has applications with electronics, or more specifically, photonics. And then it is also just the radiation that's around us, coming from the sun, coming reflected off the leaves, reflected off the ground. Uh, just it's how we see, and it's how we've started learning to use it to better our lives in the past century or so. So, just a second, why is it not going forward? There we go. So the electromagnetic spectrum. So the light is another name for electromagnetic spectrum, or electromagnetic radiation, sorry. An electric and magnetic field pushing one another forward as a wave. So light is a wave, which is why we're talking about it right now instead of waiting until after we've done electromagnetism. But because it's a wave and it has a constant speed of light in a vacuum, then that means that it's going to have a frequency and it's going to have a wavelength that's dependent on the speed of light, which is a constant, as we said. So it's going to have a frequency and a wavelength in the same way that we had ultrasonic and subsonic frequencies. When talking about sound, we have radio waves, which are obviously used to transport information through the sky. Microwaves, which are uh, microwaves, which are uh, lower frequency as well. So radio waves and microwaves are lower frequency, which means that they have lower energy. But microwaves are what we use in microwaves, where it resonates with a polar molecule, where a polar molecule is a molecule where uh, the electrons, or the positive and negative charges, are pulled away from each other. And then because of this resonance, microwaves are able to cause them to spin faster, which is going to release heat, which is going to cook your food for you. We also have X-rays in the higher frequency, which means that higher frequency means higher energy. So we have X-rays, which are used to penetrate our bodies because they have a higher energy than visible light, so they're able to go farther into the body before they're stopped. And then gamma rays, which are cosmic rays, I think, mostly, and are able to penetrate even farther. I'm not entirely sure about the cosmic rays thing, but they're definitely made by particle accelerators and have an even higher energy than X-rays. And then in that really, really small area of a rainbow, that is what we are able to see as visible light. So that's about 10 to the 15th ish, or 10 to the 15th hertz, which is about 3 times 10 to the negative 8th meters. Yeah, that seems right. So that is all that we're able to see. That is all everything else is just being discovered recently as a property of light. So this is basically just the entire presentation. It's just a couple pages talking about what light is. But a couple of the behaviors of light is that when light travels through a physical medium, its speed is always less than the speed of light in a vacuum. So it's always less than 3 × 10⁸ meters per second. And then another thing is what causes oil slicks on the ground to have bright rainbow colors. And what it is you have one, if you look at the top left diagram here, you have one one ray of light that goes that's reflected off the surface of a material. Then part of it is transferred through the surface of the material, then comes back and is refracted back to the eyes. So if this surface of the material is a proper distance, so if it's half a wavelength of light, or close to half a wavelength of light, not exactly. So if it's the proper distance, then it's going to reflect back exactly one wavelength away, and that's going to cause constructive interference, as we saw in our discussion in waves, which means that if the wavelength you're looking at will cause, so say like a red wavelength, if it's exactly this right length to be reflected and gain constructive interference along this path, then that wavelength would be a lot brighter than any of the other wavelengths which are reflected, which is why you see these bright primary colors when you're looking at light, when you're looking at an oil slick. And then polarized glasses are the last example for the day, which are just a polarizing filter. So light is a transverse if you look back here, it's a transverse electric field as a wave with a transverse magnetic field, which is the B, to its side. So because light is a transverse wave, if you put it through a slit, it's going to cut down on light if it's polarized, which means pointing in a direction that isn't in the same direction as the slit. So when you have light going through the light parallel to the direction of polarization, such as example A on our graph, then nothing happens. It just goes through the direction. It goes through the slit. It's fine. But if you have it perpendicular to the direction of polarization, then it's going to cut out all of the horizontal components that you're seeing as in dialogue, or not dialogue, as in section B, or part B of this example. And then these glasses absorb most of the horizontal light waves and transmit the vertical waves, and then the horizontal waves account for glare. So polarized sunglasses only let through the light that allows you to see more clearly. Okay, and then that's going to be it for this lecture. Thank you very much. Have a nice day.